Hello, I'm here to talk about hallucination in language models. This is joint work with Santosh Vempala at Georgia Tech. I'm at OpenAI, but I did this work when I was at Microsoft Research New England. And we all know that hallucinations are a major problem in language models, especially when they're used in high-stakes situations. What is a hallucination? Well, let's. The first point I want to make is that these models are not just hallucination is not just a property of generative language models. It's especially a property of predictive language models. What is a predictive language model? It's a model that's trying to predict what you're going to say next. And we've all used these on the phones of on our phones, where the keyboard is trying to guess and help us out, trying to predict what we're going to type next. Here's an example where I'm trying to write an obituary for myself, let's say, and it's an example from Marcus Mobius. Thank you, Marcus. The next word it predicts, the most likely word is of. Adam Clyde died of, and now then you can accept that and you can keep going and say the next word most likely is cancer. Oh, that's too bad, I died of cancer. And then it even predicts a specific date on April Fool's morning. Go figure. The worst part about dying on April Fool's is that nobody will believe you. All my friends, if my wife calls them, will think, oh no, you're just joking. This is another prank of Adam. But no, actually, the language model thinks that I died on April Fool's morning, and it's very specific, at the hospital after suffering. Oh no. Okay. So we all think this would be silly to use a language model in this way to generate text. This is obviously a predictive language model. And it seems maybe that the problem is because we're generating one word at a time. Maybe that's what's causing hallucinations, right? What is a language model? A language model is a distribution over text. In this case, I have an example here with a bunch of sentences. Now, these sentences are all facts. They all have equal probability in this example. And so this language model will not hallucinate. And this language model, you can either think of it as a distribution over text, or you can think of it as a next word predictor. They're equivalent mathematically, right? Because if we want to generate a sentence from this, we can say, okay, the first sentence, the first word is the with probability 40%. And given that it's the second word is sun with probability 50%. And given that, the third word has a half chance of being rises. And so the probability of the sun rises, which is a fact, is 10%. So these language models, you can either think of them as a next word predictor or as an entire document predictor, and they're equivalent. So if they were trained to predict documents, which they are, then they're not necessarily going to hallucinate just because they're predicting one word at a time, right? And so the way these things are trained is the parameters of a neural network are typically optimized so as to maximize the probability as a prediction of the documents that are in the training set. Or equivalently, you can think of it as minimizing the sum of the negative log likelihoods of the document probabilities or the word probabilities. It's the same. Okay, so it's not really the document prediction problem. And one beautiful thing about this is that next word prediction is really not just document prediction, it's also document generation. As I say, you can generate documents, obviously, if you have a distribution, or you can do next word prediction. You can generate an entire document, or you can actually complete the document. If I give you a prefix of a language model, if I give you a prefix of text, it will actually complete that to an entire document. And that's the way we're going to think of language models for this talk, not really as one of these chat things, but in the old way, as just a distribution over text, which can be used for conditional generation or entire document prediction. Okay. Now that we've talked about what a language model is, what is hallucination? Hallucination is such a problem that it's now a word in the dictionary, and it means a plausible but false or misleading response generated by an AI system. Let's look at some examples, because that will actually clarify and distinguish hallucinations from other types of errors. So you've all heard the statement that humans only use 10% of their brains. Well, that's a myth. That's not true, but it's all over the training data. So if a language model produces something that's in the training data that's incorrect, we won't call that a hallucination. We know where it came from. It's an error. Or a myth, as we say. And a similar example would be if it does a miscalculation. If we have a huge multiplication problem, I certainly wouldn't get this right. I don't think I'm hallucinating if I get it wrong. I made a miscalculation, an error. So we distinguish that from hallucinations, and specifically this type of problem happens when there's a system of rules, right? And in applying the rules, we make a mistake. So we're going to consider for hallucinations types of facts where there aren't a system of rules that determine what's true and false. They're kind of arbitrary. They're plausible, but we don't know where they came from. They didn't come because we violated a system rules, or they didn't come from the training data. They seem to have come out of thin air. like somebody hallucinating, for example, if they were on drugs. Okay, so what is the cause of hallucinations? That's the main point of this talk. And we're going to say that it's not just these myths. It's not just because there's noise in our training data. Yeah, that's a problem, and it's been a problem in machine learning, any kind of machine learning task. But we're going to show that models will hallucinate even if the training data has no errors, and even if there isn't a gray area. Of course, if there are errors, your model is going to hallucinate even more. We're going to give you lower bounds, so the lower bounds are going to probably be even stronger if there were errors in the training data, but we're not going to consider that, or even if there were gray areas where it could be hallucination. It's not. Okay. We're also going to argue that it's not just prompts. In the example you saw, it looked like maybe it's hallucinating because I said Adam Clyde died. Well, that's not true yet. Well, I don't know when you're watching this video. But anyway, as of the time of the making of this video, I'm still alive. And sorry. So, if you prompt it with some weird prompt that it didn't see in its training data, then, yeah, maybe it'll have to hallucinate. So we're going to show that it's not actually just the prompts. We're going to have the simplest case you could imagine. Every document in our data set will start with a single, let's say, word fact. And every time we generate, we'll condition on the generation of the single word prompt fact. So you can think of it as just a distribution of our documents with no prompt or a single word prompt. And of course, our lower bounds for language model hallucination will probably hold. It's only going to get harder if there's a weird distribution of our prompts. Finally, another problem is that the distributions are changing. You might think language models hallucinate because facts change, over time. I may die someday. And so that may make things harder. But we're actually going to show that language model would hallucinate even if the facts didn't change. So we're going to consider kind of a crazy ideal model where facts don't change, where we have a single prompt and there's no errors in our training data, and we're going to give lower bounds on how much models would even need to hallucinate in such an ideal setting. And we're going to also show that the answer, or one answer for why language models hallucinate, and I'm not saying these other reasons aren't true, is that there's pre-training. The pre-training objective itself, the way we're training these language models in what's called pre-training, as I said, to maximize the probability of the training data, that itself encourages hallucination. So what is a factoid? A factoid is something arbitrary, plausible piece of information which could be true, we call it a fact, or false, we call it a hallucination. It's not governed by some rule like multiplication. It's just arbitrary, like the date that somebody died. A major problem for language models is they hallucinate titles of articles and cases, and they give these very reasonable-looking, plausible titles of things that may or may not exist, and it's just very hard to know. Let's consider an example training data set that meets all of our ideal criteria, similar to what you might see. There are a lot of obituaries online, right? And so in this example, we imagine that the facts are stated in they're all either of two types. Either they're Alan Turing's death date, because some people are more famous. Alan Turing died on June 7th. Of 1954, or they're facts about random people and they're only occurring, let's say, once, or they're very low probability. And so we have this training set of 5 occurrences of Alan Turing's death and 5 occurrences of random people's death. And imagine that we wanted to train a language model on this data set, so we want to model this distribution. Well, an entirely plausible model of this distribution is that, with half probability, it generates the exact fact that Alan Turing died on June 7th, and with half probability, it generates a fact that a random name died on a random date for some set. So if there's m name date pairs, it assigns probability 1 over 2m. Sorry, the typo, to those. This is a reasonable language model for prediction. It's if someone's typing on the keyboard and it predicts and it suggests September for them, and it happens to be right once in a while, that'll actually save them a bunch of typing. But it's not good for generation. Nearly 50% of everything that it generates is going to be a hallucination. Okay, but it is okay for prediction. And formally, how do you measure the prediction probability? Well, in the training set, you use this cross entropy objective that we optimized. But an even simpler metric is called calibration, and that means, roughly speaking, that among the things you assign certain probability to, they should occur on average with that probability. So the things we assign probability 1 over m to should occur on average about 1 over m of the time, and that will be the case here. So even though the distribution over death dates may not be random, maybe people die in certain months more often or certain days of the week or whatever, and one could model that and further reduce that cross entropy, the uniform distribution is going to be calibrated because on average it's right the stated fraction of time. So this model will hallucinate about half the time, and That rate half, as we can imagine, if you change this distribution, it really is just depending on the fraction of facts that appear just once. That's a reasonable approximation to the hallucination rate, and that's the approximation we're going to get in our bounds. Alternatively, you could use better language models for generation. For example, you could use the language model that always generated the fact Alan Turing died on June 7th, or you could have the distribution that's uniform over the training data. Both of these are good in the sense that they won't hallucinate. They're bad in the sense that they're not even calibrated. The first one predicts probability 100% to Alan Turing die on June 7th, but the real distribution predicts 50%. The second one is way too likely on any of the random names in the training set. It'll assign probability 10% to them, whereas in reality they have a probability more like 1/m. Okay. An interesting question. So these factoids, mathematically we can model them as a set S, and we'll partition it into facts, F, and hallucinations, H. And in this case, we can draw the picture and show you. Here we're going to draw the training data in green. So the training data is assumed to be a subset of the facts. There's no errors. And then there's the facts not in the training data, which are in white. And there's many more of those than the training data. And then there's the hallucinations, where there's many more of those. And we draw those in red. Okay? And so we're assuming that the number of training data is much smaller than the number of facts, is much smaller than the number of hallucinations. So let's look at the bound here. So what our theorem says is that as long as the facts are random, okay, so this is the warm-up, the uniformly random case. If the facts are truly a random subset of the factoids and the hallucinations are the remaining, then no matter what learning algorithm you use with high probability, arbitrarily high probability, but let's say 99%, the language model you learn, let's call it D hat, has a probability of hallucinating which is almost 1 minus depending on how miscalibrated your language model is, which, as I say, language models tend to be very calibrated, so that should be a small amount. And so you should be hallucinating almost all the time. And here again, the number of training data, N, is much smaller than the number of facts, so that first fraction is tiny. And the second fraction, even though there's a 200 in front of it, there's still an exponentially smaller set of facts than things which are not true, hallucinations, things which, other versions, there's so many more dates that so many more random people could have died on than the ones mentioned here, and that's not even considering facts that can combine different things. So again, the calibration rate or the miscalibration rate is typically small, and I'm not going to define it here. But this is just a picture showing from the GPT-4 technical report. It's a slightly different definition of calibration, but they show that their language models, they're very calibrated after the pre-training phase. The math fact that kind of explains why this happens is that if a distribution is not calibrated, you can actually reduce its pre-training loss by applying some simple calibration procedure where you replace the probabilities of all documents with some other probability based just on the document probability or on the fact probability in this case. And the general theorem we have, we don't actually assume that the distribution is uniform. The facts are drawn from some arbitrary distribution, mu. And there's also, this distribution also tells us what the distribution over the facts in the training data is. And we don't need it to be uniformly random. The condition we're going to need is, roughly speaking, that the facts are regular, which means that given the training data, there's no fact which is so much more likely than average. So if we know which dates that, let's say, everyone else died on, there's no one person we can pin down and say, okay, they definitely died. They must have died on that date if this other person died on that date. But fortunately, it does allow us to say, okay, well, if Adam, Tom, and Kalai died on April Fool's Day, he didn't also die on September, 19th, right? So, okay, so that's the condition. Read the paper if you want to learn about it, but I think it's pretty reasonable. And what we can say is that for any learning algorithm with high probability, here again, the probability we assign to the hallucination set is going to be, on the left, is going to be at least a quantity which we call the rarity, or how rare facts are, which is a fraction of the training facts that appear once. Okay, so now, right, because the distribution is not uniform, so in our Alan Turing example, we were only hallucinating half the time, half the facts appeared once. Minus now the miscalibration rate, minus some other terms which are hopefully small again, assuming that the number of training examples is big but smaller than, or that the number of facts is way smaller than the number of hallucinations. Okay. This is related to something that I don't have much time to talk about called the good Turing estimator, which Alan Turing came up with, which tells you, the probability that a new fact, if we haven't seen it in our training data, that a new fact drawn the probability of a new fact would be one that we haven't seen in our training data, which is the fraction of facts that appeared exactly once in our training data, not twice. That's a totally different thing. If something appears twice, it's probably not a very, very unlikely fact. So the fraction of facts that appear exactly once is a good leave one out estimator, is the way to think about it, for the fraction of things that we haven't seen, that facts that would come up if we were to draw a new fact from our distribution, and that's key to. Okay, now let's talk about interpretation. So we're arguing that the hallucination rate from the pre-training phase should be at least the fraction of facts that appear once, the rare fact rate. And then we can think about in which domains would we expect to have lots of rare facts that appear just once in the training data. So, for very frequent domains that are discussed a lot, like the capitals of countries, that shouldn't happen very often. And it is very hard to get a language model to hallucinate about some made-up country's name of, made-up country and its made-up capital. But also, more interestingly, this one really is surprising that, these language models are really known for hallucinating the titles of even books and articles that people publish, and the point is to make those frequently. Even if my article doesn't have any citations, I'll put it on my webpage, in my CV, and my LinkedIn. And, so it's not a statistical problem for why they're hallucinating. Maybe it's a computational or a memory bandwidth or something, but our argument is not explaining that. It's not inherently statistically important for them to hallucinate on things they see many times in their training data. And you should see a high rate for hallucinations on things like obituaries or rare facts like deaths. Obituaries, somebody publishes an obituary, it probably appears just, or if they're not a very famous person, it may just appear once in the training data. Maybe most obituaries aren't even making it into our training data, but a bunch are making it there just once. And so what I want to say is that there's this post-training that we do when we take a language model and try to make it better for generation, and that actually will hurt the calibration, but it'll reduce the hallucination tremendously. So that's in the same GPT-4 tech report. They showed that, hey, after you do some calibration, post-training, whatever that is, it's RLH, who knows, whatever they do, it reduces the calibration tremendously, but they showed it also improves the hallucination rates. Okay. And lastly, I just want to conclude by kind of drawing a loose analogy to the human brain, where there's actually two language models, one for comprehension in the back near the ear, and this is a loose analogy, I admit it. But it's, you hear a lot of things, so you need to be able to process those things, and a lot of those things are facts that you didn't know about. And a lot of those things are actually things that you just don't want to generate because they're in some, other language or whatever. They're not, but you do want to understand them if a child says something. Whereas in the front of your brain, and this is similar to the predictive language model that we're generating. When we pre-train a language model, we're really setting it up for like a phone-like next word predictor because it's trained to predict what somebody's going to type next. It's not trained to generate coherent, correct things. Okay, and it is typically calibrated. But there's a second language model in the brain for production, for saying things. And if you just take that, naively take that language model which was trained for comprehension and use it for production, it would also generate nonsense. Okay? And the post-training phase takes this predictive language model and tries to change it. Kind of the miracle of language models is that you don't need to do that much. I mean, you do need to do a lot, but still, even that initial language model can be somewhat useful for generation. And with some very nice post-training techniques that people have invented, you can get a generative language model, but it's not resolved. The question of, how do we want these language models to behave is a super interesting question that we leave you with.